This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. Hello. This lecture theater, the microphone is not working well. It's not my fault. Okay, so let's try to be a bit quiet. Right. So today, in the morning, I went through position vectors. And now we are doing angular velocity vectors. Right, so after, next week your tutorial will be covering these things, position vectors and angular velocity vectors. Okay? After this lecture, the second part today will be the beginning of taking a derivative of a vector. Okay, today is quite packed. All right. So what we will be covering is I will initially speak a little bit about how to define the motion of a rigid body. So what types of velocities do we have? And then in order to define a vector of angular velocity, I will be talking about this angular rate of change. And then I'll talk about relative and absolute angular velocities. Hopefully you will be able to distinguish between them. And then the idea of summing angular velocities, and I'll give you some examples throughout. All right. So for a rigid body, we have, this is something that might be new to you if you are used to discussing just points moving. A rigid body, if I want to describe its motion, I may need to define two types of velocity. One which is linear velocity. This is something that you know, like some point where it is, in what direction it is going and how fast it is going in that direction. And I can define that linear velocity for any point on the rigid body, right? And in addition, in order to define the motion, I will need to define something called angular velocity. All right, so let's say if I choose to define for a particular, maybe this is not a very good example. This is something. I hope it won't explode. So let's say if this is a point of interest here at the center, and I want to define the motion of this body, so let's say in one example, this body can be doing this, yeah, and this point is not having any linear velocity. It is still, but still the body is rotating like that, right? So I will be able to define the motion using angular velocity. Okay, we will talk about that. Another example, this can be doing this type of motion, yeah. Still, that point has no linear velocity, but the body is moving and moving differently to the previous example, like this. Yeah, so these two different types of motion will be characterized by different angular velocities. Okay, so in general, what I'm trying to say in order to define the motion of a rigid body, we need to talk about linear velocity of at least one point on that body and angular velocity of the body. And the angular velocity of the body is something that characterizes the entire body, not any specific point on the body. So angular velocity is a characteristic of the entire body. And if there is a frame attached to that body, then the frame has the same angular velocity of the body. Okay. Yeah, so I also want to just briefly touch on different types of motion. I will not go into that in depth, okay, right now. So a body can have either purely translational motion, where it doesn't change its orientation. It can just travel in space without rotating in any direction. Okay, it can have purely rotational motion. I will not define it right now. I will define it very accurately later in the semester. And it can have what's called the general motion, where it's neither the first two. Okay, so a combination of rotation and translation in some way. I don't want to go too much in depth for the different types of motion. Just you can imagine that when we come to talk about rigid bodies, we need to talk beyond linear velocities. Okay, we need to define angular velocities to give us more information about the actual motion that the body does. Okay. So yeah, I don't want to go too much in depth for these definitions of motion. I will talk about it more in depth later. Sorry, let me change here. All right, so what you can see here is something to do with a notation that I will be using. Now the double arrow is, I will sometimes have it just as a single arrow, but in this subject, if you have something which is a double arrow, it's just to let you know that it's something to do with rotation or moment. In this case, rotation, like axis of rotation, okay, where your thumb should be pointed, and something happens about that axis. Okay, either motion about that axis, or there is this moment or torque about that axis. Okay, so that's the double arrow. You don't have to use double arrow. Okay, sometimes I don't. So this is this symbol for center of mass. Here you see point O, okay, the tree is just for decoration. This, you see R dot. R dot would stand for linear velocity, okay. R dot OG would be the linear velocity of this point G relative to point O, okay. So if I would look at the vector going from O to G, this vector would change over time as the body moves, and the change over time is the velocity vector. Okay, so this is the direction, meaning over time this point would be moving in this direction. Okay, and the magnitude of this vector is how fast it moves in that direction. Okay, it will be clear a bit later. This vector is the omega, the bold letter omega for vector, because if it's not bold, it's a scalar. So the bold letter means angular velocity. Okay, now for this one, there is a meaning of ROG without the dot. We were talking about that in the morning, right? ROG is some position vector, but there is no meaning for anything like position angular velocity. Yeah, there is no such thing. Okay, so linear velocity has like a predecessor, but angular velocity doesn't. Okay, so we will be defining angular velocities from scratch. All right, and another important thing, linear velocity relates to particular points. So I need to define linear velocity of which point, whereas angular velocity talks about a whole body. That's why I say here omega rock. Okay, not a specific point on the rock, the entire rock. Okay, it will share the same quantity, which is angular velocity. All right, is it clear? Yeah? Okay. Now, before we can actually go defining specific angular velocities, we need to understand the notion of angular rate of change. What is angular rate of change? If I have a body rotating in a particular direction or about a particular axis, the angle it sweeps is, well, some angle, let's say theta in here. The rate of change of that angle over time will be, in this case, if this is theta, so theta dot, the rate of change over time, theta dot is called the angular rate of change, okay, of that body about that axis. In this case, the axis is coming out of the page, let's say, or at least normal to the page. And this value, theta dot, is a scalar, and it will help us define the vector of angular velocity. But pay attention, it's not the same. Angular rate of change is a scalar that we use to define the vector of angular velocity. Okay? Now, when you see angles, arrows, there is always some convention, or if there is no convention, you need to define the direction of growth. Say here for theta, as theta grows, it is clear from this drawing that this rock here will be going further and further in this direction. Okay, so there should be some convention. All right, where is the positive direction of growth for that angle? So then if theta dot is positive, if it has a positive value, then it means that this theta grows in that direction. And if theta dot happens to be negative, it means that this theta shrinks. All right? Okay, so here is just an example of different bodies. They are rotating, and the rates of change, the angular rates of change, I define them as theta 1 dot, theta 2 dot, theta 3 dot, and so on. And the arrows here, they are the convention I use to say what is the positive direction. Okay, I just threw a random direction. I mean, I drew it randomly, but then I need to stick with it. So for instance, for theta 1 dot, the blue one here, this is the positive direction, okay? And it is actually rotating in that direction, so the value here is positive, okay? Let's see another one. So let's say theta 4 dot, this is what I define as the positive direction, but it actually rotates in the other way, so that's why it's a negative value, okay, in this instance, okay? And the magnitude itself also corresponds to how fast, how many radians per second the rigid body sweeps, Okay? So, yeah? Theta 2 dot should be negative? Yeah. No, no, it's fine. This is the positive direction. Okay, this is the convention. But in practice, it goes the other way. Right? All good? Okay. Sorry? All good? Okay. Now using these angular rates of change, we can go to defining angular velocities. Okay, so the first thing we are going to define is relative angular velocities. And what do I mean by relative? It is the motion of one body relative to the motion of another body. Okay, so how one body perceives another body rotating. Okay, it has nothing to do with coordinate systems or frames or how you project this vector of angular velocity. It is just one body relative to another body. Okay, so here you see these two rocks, and what you see here is omega 2, 1. Yeah, if this is rock number 2, this is rock number 1. I could also put a comma in here. Okay, it's not 21, but if you have a lot of bodies, you can put a comma. So this means the angular velocity of this body 2 relative to this body 1, or to the angular velocity of this body 1. Okay, so what does it mean? It means that relative to this body, to its motion, this one is rotating about this direction. Okay, and the rotation happens. The magnitude of this rotation is the same as the angular rate of change, as we talked about before. I'll give you examples. It will be clearer. Okay, so the magnitude is the angular rate of change, and the direction of the vector is the axis of rotation. Okay, axis of rotation of that body, or 2 in this case, relative to 1, relative to body 1. Okay, so you need to think of body 1, even though it is rotating itself, you need to think of body 1 as if it is not rotating and what happens relative to its own motion. Okay, so we'll see an example. So all the examples from the morning. All right. Now here we have two bodies, right? Link 1, link 2, and the question is to define the linear velocity of link 2 relative to link 1. Okay, so angular velocity of link 2 relative to 1. So this is omega 2, 1 in all of these cases. I wanted to show you that this relative angular velocity could be expressed in any frame you want. Okay, so what is this vector omega 2 relative to 1? Its magnitude is the angular rate of change, and its direction is the axis of rotation. What is the axis of rotation of this body relative to this body? The rotation is, or the axis is what is coming out of the slide, right? Okay, so out of the slide is Z, either in frame 0, frame 1, or frame 2. Z0, Z1, Z2, they are all parallel coming out of the slide. And so I'm having just that last component. And beta dot is the angular rate of change. What do I mean by that? If you kind of freeze body 1, freeze your link 1, how does link 2 rotate relative to it? Just by increasing that beta. So if you follow along this beta direction, yeah, it goes, the axis of rotation is aligned with your z, right? Z0, Z1, or Z2. So you have a positive, or you have here just beta dot, not minus beta dot. Okay, so in other words, if beta increases, or beta dot is positive, you will have here a positive relative angular velocity, yeah, of link 2 relative to link 1. Okay, is it clear? So? Okay, we'll see more examples. Any questions about that? Okay, let's look at this 3D example with the wing. Okay. Remember the example from the morning? So the question is to define the angular velocity of this wing, link 2, relative to link 1. Okay, so how my hand is rotating relative to my body. Okay? So wing relative to torso. Okay? So this relative motion, you can look here, beta is the angle that defines that relative motion of link 2 relative to link 1, right? It's captured by this angle beta. So what is the axis of rotation? Look here, if this is y2 and z2, where is x2? Going in, right? Yeah, so if x2 is going in, but if you follow your fingers along this convention, this arrow for beta, it is opposite to where x2 is going, right? So you have this minus beta dot, okay? So minus beta dot would be the angular rate of change, and the axis is the x, okay, or beta dot and negative x. Overall, you can write it like that. So this thing you read here like this. This is the vector of angular velocity of link 2 relative to link 1 expressed in frame 2. Okay? What do I mean by expressed in frame 2? I am writing the components of this vector along the axis of this blue frame 2. Okay? Can I express this vector in frame 1? Yes. Okay, so this is the angular velocity of link 2 relative to link 1 expressed in frame 1. You see here? 1, all right. How to transition? So you need to, well, you can just use rotation matrices as normal, right? And just rotate your vector from here, this one, with the rotation matrix from 2 to 1, and you will get the result in frame 1, right? But because the rotation matrix is about x, and actually frame 1 and frame 2 share the same x direction, right? It's the same x, x1, x2. You get the same result, all right? Can you do omega 2 relative to 1 in frame 0? Yes. What will you need to do? Just, yeah, multiply with the rotation matrix from 1 to 0, one more, right? And this time it looks like this. Okay, this is the rotation matrix from 1 to 0. Okay, so you plug it in, okay, and this is the result. So what is this? This is the angular velocity of link 2 relative to link 1 expressed in frame 0. Okay, so you can see it has 2 non-zero components and 1 zero component. Right, the 2 non-zero components are along the x0 and y0, because if you think about the motion of link 2 relative to link 1, yeah, you don't take into account anything that happens about the z, because whatever happens in the z is just the link 1 motion, yeah, this one. So if you freeze the motion of link 1, you just have link 2 relative to link 1, yeah. Everything is about this axis, yeah. And so this axis would be projected only onto x0 and y0 in frame 0, nothing on the z. Does it make sense? Okay, because it's a relative angular velocity. Okay. Okay, now what if I want to calculate absolute angular velocity? So I gave you here this example. The red one is the relative angular velocity, as before, of this rock relative to this rock. This would be the absolute angular velocity of this rock, and this would be the absolute angular velocity of this rock. So you see only one index. So 2 means like 2 relative to 0. 1 means like 1 relative to 0. 0 being the stationary space, something that is not moving at all. Okay, so absolute is just like relative to the non-moving space. Okay? So not relative to some moving body, but relative to, say, the still, non-moving ground. Okay, that's it. Okay. Still, you can represent absolute angular velocities in any coordinate system, in any frame. Okay, because it is still a vector with direction and magnitude, just like any other vector. You can represent it in any frame you want. Okay, so is there any questions so far? All right, so let's practice a little bit. Oh yeah, before the next slides, I want to, yeah, this is super important. How do you, so in this example, if you want to calculate this omega 2 or absolute angular velocity of rock 2, what would you do? You would need to sum this vector omega 1 with this vector omega 2 relative to 1. Okay, just like with linear velocities, if you have say 2 cars and you say this car is going 20 kilometers per hour faster than this car, yeah, and this car is going 60 kilometers per hour. So what is the absolute linear velocity of this one? So you just sum them, right? This is the same. You just sum them. It's an absolute plus the relative to the previous one. Okay, so it's a normal summation. And here is another example. You can think of these absolute and relative angular velocities as just normal vectors. If you need, say, if you have body number 4 and you know the angular velocity of body 4 relative to body 3 and angular velocity of body 3 relative to body 2 and so on, you can calculate the absolute angular velocity of body 4. Okay, so you will just sum it like this. Okay, just like you would sum vectors. Okay, so omega 4 is omega 1, or 1 relative to 0, as I said, plus 2 relative to 1, plus 3 relative to 2, plus 4 relative to 3. Okay? Just think about these cars, okay? Going, one having its absolute linear velocity and the rest compared to one another. All right? Okay, so back to this example. Now the question is to find the absolute angular velocity of link 2. Absolute angular velocity of link 2. So what to do? We need to sum the angular velocity of link 2 relative to link 1 plus the absolute angular velocity of link 1. What is the absolute angular velocity of link 1? This is easy because link 1 is moving with angular rate of change alpha dot with respect to the non-moving space, right? And axis of rotation is z in any of the drawn frames. Okay? So this thing here is the absolute angular velocity of link 1. Okay? And this one is link 2 relative to link 1. Okay? So if I sum them, I get the absolute angular velocity of link 2. Okay? In this case, I chose to represent it along the axis of frame 1. Okay? Okay, so it's a vector which has just this one non-zero component, the z component or z1 component, yeah, because it's frame 1. So z1 component is alpha dot plus beta dot. Okay, that's the absolute angular velocity of link 2. If you want to check, imagine that everything other than this link 2 is dark, everything is blank, disappears, and you only have link 2, okay, performing its motion, and alpha and beta are changing. Okay, so as alpha and beta are changing, link 2 will be rotating with the rate of change relative to the ground, to the stationary space, with alpha dot plus beta dot. Okay, so either of them changes, this will rotate. Okay, if you freeze your beta, but alpha is changing, still link 2 will be moving, right? Okay. Any questions so far? Okay. Is it clear? Yes. Okay, this example now, absolute angular velocity of the wing, or link 2 here. Absolute angular velocity. What do we need to do? We already found its relative angular velocity relative to link 1. Okay, so what is the absolute angular velocity of link 1? Absolute angular velocity of link 1 is this. It's alpha dot in the z1 or z0 direction. Here it's represented already in frame 1. Okay. Why is this correct? Because this is the motion of this link, link 1, relative to the non-moving space. Okay? Just depends on this alpha angle. Okay? Alpha dot is the rate of change, and the direction or the axis of rotation is the axis that comes out of this drawing, so Z0 or Z1. All right? And now this one we had before, remember? And now we can sum them in the same frame. Okay? In this case, frame 1. Okay? So this is the result. Minus beta dot, 0, alpha dot. Okay? how do you read this thing? This is the absolute angular velocity of link 2 expressed in frame 1. All right? Can you express the absolute angular velocity of link 2 in frame 2? Sorry? No, it wouldn't be 0. So how to get this? Omega 2, absolute angular velocity of link 2 in frame 2. If we already have this one, we simply need to multiply by the rotation matrix from 1 to 2, which is the transpose of the rotation matrix from 2 to 1. Okay. Otherwise, we have other ways to find it. Okay. So, for instance, you may first find omega 2 relative to 1 in frame 2. What would it be? The same as this one, remember? Minus beta dot along the x2 direction. Okay? And then add it to omega 1 in frame 2, or in 1 and then rotate it to 2. Okay? That's okay. What we will do now is, so here is the next example. The question here is to find the absolute angular velocity of the wheel. Now, absolute angular velocity of the wheel. And notice how which frame is attached to the wheel? 3, right? So it is the same question as what is the absolute angular velocity of frame 3. Okay, because frame 3 and the wheel are like one rigid body, one body. So what I will do is sum the absolute angular velocity of link 1, which is this T-shaped bar, link 2, which is link 2 relative to 1, angular velocity of link 2 relative to link 1, and angular velocity of the wheel relative to link 2. Okay? So maybe so if I'm asked to find absolute angular velocity of the wheel or frame 3, which is attached to it, in frame 1, I will need to sum absolute angular velocity of link 1 with link 2 relative to 1 with link 3 relative to 2, okay? Or you can put these things. Some students, I know, they like putting 0 like that, okay? Same. 0 is like nothing. So, and if I want it in 1, I need all of them to be like that in 1, okay? But they are not simple to find in frame 1, so I may want to find this one in frame 3 or 2 and then rotate to frame 1 and similarly rotate to frame 1 gradually. All right? So have a look at these. This is the absolute angular velocity of link 1. This is the angular velocity of link 2 relative to 1, and angular velocity of link 3 relative to link 2. Okay? And they are calculated here in different frames for convenience. Now remember, I told you the omega is normally standing already for angular rate of change. So it's not an angle, that's why I don't write omega dot. So omega about the y1 direction. Okay, that's the rotation relative to the still space. Okay, now beta dot, this is beta, beta dot about the z2 axis would be this relative angular velocity. Okay, can you see that, guys? Beta dot in the z2 direction is the angular velocity of link 2 relative to link 1. Okay, and then the wheel has angular velocity gamma dot in the x3 direction relative to this bar, link 2, this rod. Okay, so now in order to sum all of them, I need to unite the frame. All right, so I'm doing it all in frame 1. Okay, so this one is already in frame 1. This is in frame 2, so I rotate from 2 to 1. And this is in frame 3, so from 3 to 2, from 2 to 1. Okay, and the result is in frame 1. Okay, so this is the calculation, the specifics. All right, let me know if you have any questions. No questions? Do you want me to bring back the previous slide? Yeah. Okay, no questions. Yeah. Can I find, so remember we found here omega 3 in frame 1. What if I wanted to find omega 3 in frame 3? What would I do? So if I want it in frame 3, yeah. So this one, what is it in frame 3? Remember, this was gamma dot about the x. So gamma dot 0, 0, like this, right? So it's already in frame 3. This one, let's say I can do it in frame 2. 2 relative to 1, and then rotate from 2 to 3. Okay. And this one, what was it? It was beta dot in the z direction, I think. Right? What is this one here? Rotation matrix from 2 to 3. So from 3 to 2, let me check. So from 3 to 2, we have rotation about x positive. So the transpose of that will be just like the negative x rotation about gamma. Okay? And similarly, you will need to work on this one. So just put here omega 1, or 1 relative to 0, in frame 1, let's say, and then rotate it from 1 to 2 and from 2 to 3. Okay? Is it clear? Okay. So let's go to the next example, the last example, this wheel. If the question is to find the absolute angular velocity of the wheel, absolute angular velocity of the wheel, right? Remember, we attached which frame to the wheel? Frame 3. Right, the green one. The blue one is attached to what? The shaft, the tilted way, right? Now, so essentially we need to find this omega 3, and if we want, we can find it in frame 0. So its components in the black coordinate system. Okay, absolute angular velocity of the wheel expressed along the black axis. If I wanted, I could also express the same vector, right, in any other coordinate system, blue, green, red, any. Okay? So just to reiterate, the word absolute for absolute angular velocity has nothing to do with the frame in which I represent the vector. Okay? Is it clear? I can express an absolute angular velocity along rotating coordinate system axis. All right? So we would need to sum, again here, angular velocity of this frame 3 relative to 2 plus 2 relative to 1 plus 1 relative to 0. All right? Let's look at these angular velocities. So 1 relative to 0, can you see why it's negative omega in the y0 direction? So this rotation here, you see that there is a bit of red in here, which means you go like this, okay? So the rotation is about the negative y0 direction. Okay, so minus omega. Any questions? And why is this 2 relative to 1 all zeros? Sorry? Say again?
They're rotating about the same axis, they're not actually on the relative axis.
Yeah. So frame 2 and frame 1, they are both attached to the same body, the shaft, right? They rotate about the same axis. Both of them rotate about the negative y0 axis, both of them. They are just tilted one with respect to the other, but this tilt is a constant change in configuration. So don't put alpha dot anywhere here, because alpha dot is 0, as I mentioned in the morning session. Okay? And finally this one, minus beta dot along the y2, okay, direction. Is it clear? All clear? So this is just the substitution of the rotation matrices and final calculation. For your practice, I suggest calculate omega 3 in frame 1, omega 3 in frame 2, omega 3 in frame 3. Okay? Just do some practice about it. All right? So that's the last slide. Let's take a little break, and then we continue with the next topic.
the rotating disk. Omega 3
Yeah.
in frame 3.
Yeah. Yeah.
Confirm it.
Yeah. 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 Yeah.
Wonderful. Thank you.
Just substitute all the values now.
Yeah, of course.
Do you want to keep going? Yeah. All right. So what we've covered today so far will be in the tutorial next week. All right. This is quite fundamental what you have so far. In terms of linear motion, position vectors. In terms of angular motion, angular velocities. Okay. These things you find from scratch. And then in order to continue towards setting up Newton-Euler equations, you will need to know how to take a derivative of a vector, which is represented in a coordinate system, which is not like zero, it's a non-moving coordinate system. If you have like what we did, say omega, some kind of angular velocity expressed in frame 3, and frame 3 is moving, changing its orientation, how to find this omega dot, or the derivative of that vector, okay? So you will need to know a very basic formula that we will be using throughout the subject after this double lecture. And this formula is doing one thing, taking a derivative of a vector, all right? And it's applicable always. If you have a position vector and you apply that formula, you get the velocity vector, okay? The corresponding velocity vector. If you take the velocity vector and apply that formula, you get the corresponding acceleration vector, okay? If you take angular velocity vector and you apply that formula, you get angular acceleration vector, okay, and so on. So this is a really useful formula. What we are going to do, because we are talking about derivatives, we are talking about change versus time. The derivative here, I mean derivative with respect to time, okay? You are used to working in a stationary coordinate system. Okay, nothing is moving, and so if you have a vector and you want to take a derivative of that vector with respect to time, you just go component by component and take the derivatives of each component, right? And this would lead to a mistake if you do the same for a vector expressed in a rotating coordinate system. Okay, so I want to illustrate the mistake. So this will be done in this naive example. Sorry, I need to, sorry. Yeah, so this naive example will do the wrong thing so that you will learn what not to do, all right? And then we will rectify it, okay? We will see what does work. And then we will start developing that formula, deriving the formula for getting a derivative. All right. I just remind you this lecture is quite long, so we will do part of it today, and next week we'll continue. Okay. So what is this example? Imagine point A is fixed. Okay, it's a fixed axis of rotation, and there is this. Well, you can think of it as a disk rotating about this point A. Okay, which is a hinge. And there is this point B on the perimeter of this disk. Okay, so B is rotating with this angle theta, or angular rate of change theta dot. Okay, about, in this case, axis Z1. Okay, so the question is to find the absolute linear velocity of point B. Okay, absolute linear velocity of point B. Now, in terms of position, the position of B relative to A. Now, when I say relative to A, I mean absolute, because A is stationary. Okay, so the absolute position of point B is, you can look at it as R00 along the red axis, okay, frame 1. Okay, so R in the x1 direction, okay? Or in the black frame 0, it will be R cosine theta and R sine theta, sorry, R sine theta, yeah, R cosine theta, R sine theta. Okay, as in terms of position. So in order to get velocity from position, how to take a derivative? Now, remember that frame 0 is fixed, stationary, or we call it sometimes inertial. It is not moving. So if I would take derivative, as you know, for this vector, RAB in frame 0, if I will take the derivative, the first component would be minus R sine theta times theta dot, okay, according to the chain rule. Second component would be minus R cosine theta times theta dot. Sorry, no minus, R cosine theta times theta dot, okay, and then 0. That will be fine. This will be the correct velocity vector of point B, okay? Linear velocity of point B. But if I do the same component by component derivative for this vector, I will get 0, 0, 0, right? But 0, 0, 0 is not the velocity of point B. Okay, now you can start thinking, yeah, but this is what frame 1 thinks that point B is doing. Okay, if you're sitting on frame 1 and moving with frame 1, for you, you perceive point B as stationary. But this is not what I asked. I asked, what is the absolute linear velocity of point B? Okay, not how it is perceived from some moving object. Okay. So let me just show the slides for what I've been talking. So this is fine. This is correct. This is doing the, I call it term by term or component by component derivative. If you do it in a stationary or fixed frame, this is fine. This is correct. Okay, so this is the absolute position of point B, and this is the absolute velocity of point B in frame 0, expressed in frame 0, and this is correct. If you are doing it in frame 1, this is incorrect. Okay, so this is to demonstrate what was here, how to fail the subject for sure. Okay, so don't do that. okay, the dot here stands for actual change with respect to time. And this point B, it does change its position when time goes on. Okay, so when when time changes, theta can change, right? And point B would be moving. So this motion should be captured in the absolute velocity of point B. Okay, now maybe I'll keep going forward. Yeah, so what you want to have in the correct approach, you want these two vectors RAB dot in frame 0 or frame 1 to correspond to the same physical quantity, same direction and same magnitude. Okay? The velocity vector is just like any other vector. It has direction and magnitude, and you can express it in any frame you want. So what you want here is to be able to transition from the representation in frame 1 to the representation in frame 0 just using a rotation matrix. Okay, right now you cannot do that, right? It's wrong, therefore. Okay, so what we are after is some method to take correctly a derivative of this the position vector RAB, take its derivative with respect to time, and get the velocity vector of this point B expressed in frame 1. Okay, and it will not be all zeros because it should have the same magnitude as this one, okay, which is non-zero. All right, are you with me, roughly? Okay, we are searching for the actual velocity vector of point B, absolute linear velocity of point B, and we would like to express that velocity vector in frame 1, that is along the axis x1, y1, z1. All right? Right now you can get it by rotating this, or by multiplying this vector by the rotation matrix from 0 to 1, right? But I want to get it directly from RAB. Okay, now where is the mistake that happened before? What you are doing here, if you are doing this, essentially you are ignoring the information hidden inside this 1, the label 1 here, the index 1. Why? Because this 1 means along the axis of frame 1, they themselves are moving with respect to time. So there is some change in time hidden inside this little 1, right? So you need to take it into account. Okay? Now, look at this formula here, this equation. So this V here, this V stands for a vector in general, just any vector, not velocity, any vector. So this V is expressed in frame 0. Imagine, for the sake of this lecture, frame 0 to be always a stationary frame. And this F stands for a frame other than 0, so a rotating, a moving frame. Okay. Now, the inside of the brackets here is equivalent, right? So I can rewrite V in frame 0 as V in some other frame F multiplied by the rotation from F to 0, right? So the inside of the brackets is fine. What we did the correct way was to take the component by component derivative of the position vector R from A to B in frame 0. So that was fine. All right. Now, in order to open the brackets here correctly, take the derivative correctly, I need to apply the rule of derivative of a product, right? So it would be, say, this rotation matrix times the derivative of the vector plus the derivative of the rotation matrix times the vector. Okay, and this part is what we didn't do. We didn't take into account the rotation matrix from 1 to 0 changing with time, okay? Because it does have some sines and cosines of theta hidden in it, okay? What we did do is just this part. We took the derivative of r from AB expressed in frame 1 directly, okay? So we ignored the change over time of frame 1 itself. Okay, so in order to not ignore, we will need to add this part. Okay? So let's look how these things become all right. This is what we did here. Okay, in the previous example, right? R00 was RAB in frame 1. Okay, so that the derivative component by component is just all zeros. Okay, so it's lost. And R00 is the vector we are trying to take the derivative of, okay, in frame 1. And this part should be the component by component derivative of the rotation matrix from 1 to 0. Okay, what is the rotation matrix from 1 to 0? So it's just positive rotation about z. All right? So this is the derivative component by component of this positive rotation about z. All right? By now, I hope you remember by heart all of these rotation matrices, the common 6 ones. Okay, so cosine theta becomes minus theta dot sine theta, and so on. All right? So if we substitute this derivative of the rotation matrix, we get this. Okay, so this is this, okay, and times this. We get the correct thing, which we got before, the component by component derivative of RAB in frame 0. Okay, this is just like a sanity check that it works. Okay, so in order to kind of get the derivative in frame 1 directly, we could either do it in frame 0, then rotate from 0 to 1. Okay, but I would like to avoid it and find a formula that I can apply in frame 1 only, directly in frame 1. And in order to do that, I will be first proving this property. Don't worry, I will simplify that for you. First of all, look at this part. d dt r from f to 0 times the vector in frame f. This part, okay, memorize it. It is these two, okay? So these two pre-multiplied by the rotation matrix from 0 to f. Okay, this will make here essentially everything in f, frame f. Okay, now instead of talking about frame 1, I'm generalizing it to any frame that is not 0, okay, or 0, but in general, any frame. And on the right-hand side, this is what I want to prove, that this expression is equal to this expression. Here, everything is already only in frame f. So we will be eventually finding a formula for a derivative of a vector that you can apply in some frame f that is potentially rotating. What is this omega f in frame f? We already spoke about angular velocities. This is the absolute angular velocity of frame F expressed in frame F, expressed along the coordinates of the rotating frame F. Okay? The angular velocity of frame 3 expressed in frame 3. Okay? Something like that. And this one here, V, expressed in frame F, would be some vector that we would like to take the derivative of. Okay? Any vector that we want to take the derivative of expressed in frame F. Okay? So before we obtain the formula, the final formula, this is the equation that I would like to prepare. Okay? And then I will use it to quickly get the formula. All right. You already see that this part appeared in the derivation by parts. Sorry, not by derivation of a product. Okay? So we have here this red axis to stand for some frame F, that is moving, okay, rotating, changing its orientation. And this omega F corresponds to the absolute angular velocity of this frame. All right? Expressed along these red axes. All right? Because it's a vector. Is this a unit vector? No, not necessarily. Okay? It means that this red frame rotates about this direction, and the speed of that rotation depends on is the same as the magnitude of this vector. All right? Okay. Any questions? Do you all understand what is the purple omega F in frame F? Raise your hand if yes. Hi. Okay. Do you want me to repeat? Because most of you didn't raise, yeah? So, okay. Let's go back to this example. Here we have frame 1, which is the rotating frame. Okay, so F stands for 1 in this example. All right? What is omega 1 in frame 1? What is the axis of rotation of frame 1? Z0 or Z1? Yeah? Z1. What is the angular rate of change? Theta dot, right? And the direction is aligned, so it will be 0, 0, theta dot. Okay, so omega 1 in frame 1 is 0, 0, theta dot. All right? So now, in general, if we look in a general 3D case, we have some frame F that is moving, changing its orientation, rotating. It has some instantaneous axis about which it rotates. This axis can change over time. Yeah, this omega F is not a constant. It can change over time. And it has its speed of rotation about that axis. And that speed, just like theta dot in the previous example, is the magnitude of this vector. Okay? Now this vector of angular velocity of that frame F, this vector I can express in any coordinate system I would like. In particular, I can, if I want to, express it in the same frame F. So along the red coordinate system. Okay? Now, in order to do that expression, I I drew here the components of this omega f. Okay, so I projected omega f onto xf, yf, and zf, right? So omega f is simply in frame f is just omega fx. That's not good. Omega f in frame f, the vector is omega fx, omega fy, omega fz, right? In another frame, it would be something else. All right? Got it? So these are the components, okay? What I'm going to do now that I have the components, I'm going to just omit the sum of these components, the omega f itself. I'm just going to leave the components, all right? The projections. Okay. So I remind you that this red coordinate system, frame f, is rotating, right? The next time instant, it will not be pointing where it pointed right now. It would change its orientation, right? Change and change and change. Okay, so if I want to find out what is the direction of the red axis after some short delta t time, what I can do is do superposition of rotations about x, about y, about z. Okay. For example, this one, this component of the angular velocity of the frame. Remember, angular velocity of the frame tells you how the frame rotates over time, or rotates in a specific instant. All right. So this component says there is this motion about this axis, okay? And it means that yf will move slightly upwards and zf would move slightly into the slide, okay, around this omega fx, okay, or around xf. By how much? If I just let time pass by a short delta t, okay, so it will be delta t times this scalar omega fx. Okay, so there would be an arc here with that angle, omega fx times delta t. Okay, some arc and some arc here for the z. Okay, so I put here alpha as omega fx times delta t. Okay, this is the angle here. Okay, this is how much axis yf and zf would sweep as a result of the rotation from this component. Okay, so I'm doing here some superposition of the different components. All right, so any questions so far? Is it clear? Is it clear? Yeah. Okay, now the arc here, it's not a straight line, but if delta t is really, really, really small, we can approximate it with a straight line. Okay, I will do it later. And now let's look at the rotation of the axis as a result of this omega fy component. Okay, what would it contribute? Z and x to rotate about the y, all right? So I represent this rotation using this blue axis, okay, and the angle beta. So what is beta? It is omega Fy, okay, the radians per second, times delta t, the amount of time that passed. Okay? And finally, as a result of this component, the z component, axis x and y would sweep some angle on their plane. Okay, so x would move with some gamma, which is this, okay, omega fz times delta t, and yf would move with that gamma to here, okay, on the plane. So I just decomposed the change of orientation of that red frame f according to the different components of the angular velocity. Okay, now I need to combine everything back to find out where would the axis, where would xf, yf, zf be after that delta t time. Okay, so how to find that? So what we will do is combine all the contributions, assuming that the arcs are straight lines. Okay, so for very small delta t, okay, this arc is nearly the straight line that is of the size of that arc. Okay, now the length of the arc, if you have an angle in radians, the length of the arc is the angle in radians times the radius, right? The radius here of the sweeping, let's say, the radius is the unit vector. Okay, so it's just 1. So essentially the arc length is the same as the angle in radians. Okay? So where would, I will bring this up. Where would the new axis xf be after the delta t time? Kind of here. Okay? It would move downwards, this beta in radians, and to the right, gamma. Okay? And what does it mean downwards? It means in the negative zf direction. And what does it mean to the right? In the positive yf direction. Okay? So if I want to go from the origin to the new position, yeah, that would be my xf at t plus delta t. Yeah. What I need to do is go xf, the original one, at time t, then go against the z direction by beta radians, and then go along the y direction by gamma radians. Okay, so this is the summation I'm doing at the top. I start with the original. I'll hide this to not draw on the wall. Original x, then beta in the negative z, so minus beta z, okay, and then plus gamma y. Okay, I will arrive at the new orientation of xf after delta t time. Okay? Is that clear? No, normally I give like a minute for people to discuss, explain to one another. Is it clear, guys? Raise your hand if not. Oh, clear. So I'm asking, and then you give me the impression that you're so smart, and then I build difficult exams. No, I'm kidding. You pretend that you don't understand if you want an easy exam. Okay, let's look at how YF is oriented after delta t time. Okay, so I need to move up by alpha, so that's alpha in the z direction, and to move inside by gamma radius, so inside is against the x direction. Okay, and z after delta t. Okay, maybe have a look. All right. Now, why do I need all that? I'm going to look at the, I'm going to compare something to do with derivative, okay, derivative of a rotation matrix. And if you remember, a rotation matrix is composed column by column from the axis. So if I look at the rotation matrix from f to 0, that is xf in 0, yf in 0, zf in 0, right? So the derivative of this one would be the derivatives like this, okay? These three derivatives. We are going to look at the derivatives of these axes. And by that I mean how they change with time. All right? How they change in time. So I'm looking at some delta t, and then in order to get the derivative, I'm going to approximate this delta t in the limits that it goes to 0. Okay, so step by step, to the next step, I just substituted alpha, beta, and gamma with their actual expressions. Okay, so alpha is this, okay, beta and gamma. And now I'm going to shift the x, y, z to the left-hand side. Okay, I'm going towards getting the derivative of the axis, x, y, z. Okay, maybe you can already see what's going on. Next step would be to divide by delta t, right? Dividing by delta t. Why is it approximated here and not equal? Because so far delta t is just a small value, but not yet approaching 0. So I just approximated the lines with the arcs. Okay, when delta t is approaching 0, then I can move to equal. All right. Okay. And now instead of this one here, I was requested by some student who couldn't attend the lecture to not use the laser pointer. I'm so used to it, instead of doing this, I just come myself. So I'm sorry, I'm trying. Instead of this, what can I write using calculus? ZF dot, the derivative of ZF, right. So this is the change of the ZF axis over time, okay? So for instance, if ZF is pointing there, the next moment it goes there, yeah, like that. this is the derivative vector, okay? This is the direction and some size, okay? If it's faster, then the derivative vector will be longer, okay? And slower, it will be shorter, okay? But in this direction, okay? So separate, okay? So I just replace them with the dots, x dot, y dot, and z dot. Okay, is it clear so far? I feel that I'm frying your brain. That's fine. Okay. Okay, now these are vector equations, and they are quite interesting. Let's pause a little bit. The colorful things are components of the angular velocity vector that is, projected, angular velocity of frame F projected onto the axis of frame F. So, yeah, omega x, so omega fx, omega fy, omega fz, okay? And here, these are the changes of the axis over time expressed using the axes themselves. So let's say xf dot, what I just said, if this is xf, okay, next moment it's here, so xf dot is like that, okay? It is some combination of yf and zf, okay? So if yf and zf are like this, some combination of these directions, and that combination depends on omega fy, omega fz, okay? Now, these vectors, xf dot, which is a vector, zf, which is a vector, yf vector, these vectors, I can express them in any coordinate system, right? So just like I did here, I can express them in frame 0, for instance. Okay? So this is what we are going to do here. So if I just rewrite these equations, which are correct in any kind of frame, you can represent all the vectors in any frame you like. You can do that in frame 0 also, right? When you do it in frame 0, these three vectors, yeah, will be like dot, dot, dot. Okay, so this will be the time derivative of this vector. Okay, so we are going towards what we wanted to get. Okay. Like that. Okay, you can just, does this make sense to you guys? Because the rotation matrix from F to 0 is X, F, Y, F, Z, F projected on frame 0, as we learned last week. Okay? If you take term by term derivative of this rotation matrix, it's like taking term by term derivatives of these vectors. Okay? You are doing that in frame 0. So you are doing essentially what we did in the at the start when we did our AB dot in frame 0. I told you this is fine. When you take term by term derivative in frame 0, it's fine because nothing is rotating, so you don't need to compensate for any rotation. Okay, so if you do d dt of that, okay, term by term, it's like just putting dot, dot, and dot here. Okay, so this is what we have here. Okay, so I can just substitute it this way. Okay, so far? Any questions? Okay, now this was in frame 0. Okay, let me put it like this. So, and then I pre-multiply it by this rotation matrix. Why? Because I want to get to the left-hand side. Maybe I'll remind you where we started or what we want to prove. Oh, here. So we spoke about this part, which is here, right? This part. And now I want to pre-multiply it by the rotation matrix from 0 to f. Okay? Eventually, I'll also multiply it from the right with some vector in frame f. Okay? So going there, oh, too much. Yeah. Okay, so here, pre-multiplying this derivative of r from f to 0 with the rotation matrix from 0 to f. Okay, and what I can do algebraically is just do it each of them. Okay, I can so the resulting matrix would have its 3 columns like this. Okay, I can just pre-multiply each vector by this matrix to create the new vector here. All right? Now, what is the result of this? X dot f in frame 0 pre-multiplied by rotation matrix from 0 to f, I get x dot in f. Okay? And so on. Okay, y dot f in f, z dot f in f. Okay, now what can I do? I can go back to these general formulas, and just like we applied them in frame 0, we can also apply them in frame f. Okay, so try to maybe rewrite that in frame f. Okay, so in frame f, it's a bit more special. Okay, why? Let's look at this one, for instance. Yf in f. What is yf in frame f? 0, 1, 0. Okay? That's how you express the unit vector pointing in the yf direction in frame f. Okay, so xf in f is just 1, 0, 0. Okay, so we can substitute all that. If I want to express the first one, xf dot in frame f, let me substitute instead of z f in f here 0, 0, 1, and here 0, 1, 0, and these are scalars. Okay, so I keep them as scalars. Okay, so here is the substitution, and this is the result, the resulting vector. Okay. Similarly for y, so essentially I'm going to substitute this into here. Okay. Now we are far away from dynamics. We are deep into algebra. Okay, but be patient. We will use the end result very, very frequently. Okay, for the y, I'm using the y dot. Okay, for the z, z dot. And now these are the 3 results. I'm going to substitute into here, into the columns. All right, are you following? Someone is following. That's good. Okay, substituted the 3 columns. This is what I get. Okay. Now, to prove what we had to prove, I need to also add here this general vector vf. Okay. Okay, so all of this matrix here multiplies vf. And now I kind of jump and say this is equal, so this matrix times vector equals this vector cross this vector, cross product this vector. Why? Because it works, all right? You need to try it. It's a property from algebra. Instead of doing a cross product, you can take the first vector and just spread its components in a matrix, in a skew symmetric matrix like this. Okay, so in order to check that, just to check it, maybe instead of this V, sorry, so put here Vx, Vz, this is not bold, yeah, and take the cross product and get something, okay? Solve it. And then do the same for, well, there, okay? And do the matrix multiplication. Matrix times the same vector. Okay? And then you will see that you're getting the same expression. That's it. Okay? Nothing fancy. And from here, I get this one, which is, we recall, angular velocity of frame F expressed in frame F. Why? Because these were its 3 components, okay, along the axis. All right? So we proved that property. That was the boring part, all right? And, yeah, so this is the summary. I think you guys are fried enough. I'll let you go at this stage, all right? Next time we start from here. Thank you. Have a nice weekend.
I went to the MATLAB class last night with David. The ODE. Why don't you do a chance to do another maybe class to do animation? So I know we're going to have to do a little bit of that later in the semester.
Yeah.
Can I email him?
I will ask.
Okay.
Just to remind me.
Absolutely. No, thank you. Gabriel. Thanks.
Just a quick question. So I was wondering how important it is to remember the move, because I tried really hard to like follow, and then like I'm kind of scared that I don't know remember every step. So I just need to understand the concept. Okay. Thanks. That's hard.
So here, do you have something I can write with? So look at the direction of this omega. Do this. Your thumb is to the left, right? Whereas this y0 is to the right. Okay, so this rotation is in the negative y0 direction or negative y1 direction. So it is, that's why it's minus here.
Similarly for this beta,
Yes.
since it's like this.
Yeah, in the negative y3 direction. Yeah?
Thank you. This is angular velocity, and this is
No, this is angular rate of change because it's a scalar, right?
yeah,
Scalar, yeah.
angular rate of
Change. Yeah, it's like we had alpha dot, beta dot, things like that.
Yeah. So R
Same radians per second.
yeah. So R is
Because
by
angular velocity is a vector. All right?
yeah.
yeah, it's a scalar, and
Yes.
the alpha is an angle.
Yes.
Okay, so here the angle to multiply
Yeah.
a light current and vector.
Yeah, I will explain. Yeah, because
Select direction.
So she told me that for this link is like this. Okay, and with reference to the y naught axis, y naught is in this direction. So when you hold the thumb, it's like this. So it's like this.
Yeah, but
Y
this
is
is
so negative.
you're asking why your
She told me that.
So that's for okay. For beta,
So now again for beta, hold it like this.
x to no go from z to x.
No, not
Negative and y, no? So basically it's negative.
No, not to axis. It's like beta is like this, right? Beta is going like this. Yeah. So your thumb direction like this, but which is opposite to direction of y. About which you're rotating. That's right.
So why are you standing?
that's why I put here approximate. Okay? And then later when delta t is approaching 0, the angle will be so small that arbitrarily small.
So beta here is actually
Did you understand what I said about the r equal 1?
so beta is some kind of distance here. So very
Yes.
small, it's very small distance. It's wrong.
Yes. I will draw it better. So, let's say this is of length 1. Okay? And I have some very short delta t. After that very short delta t, this moves some kind of beta here. Okay, so this r is beta times 1 meters. Yeah?
Like
And then approximately straight line. Yeah.
Thank you. Thank you.
Thank you. Weekend well deserved.
Yeah. Tough meeting with Colin.
Why is he
So like drafting
Unhappy.
papers.
hydrogen paper?
Like tens of hundreds of comments I need to address.
But it's good, hey, because he's responsive.
Yeah,
He
he
tells
is.
you.
Yeah.
Some
yeah,
supervisors
yes,
ignore you.
yes.